All right, it's time to go. Welcome to this presentation, Asynchronous I/O and Coroutines for smooth data streaming. I'm afraid I was a heck of a lot more optimistic when I wrote the proposal than I am right now, so you may feel a little bit deceived at the end of the presentation. Apologies. I'm Björn Fahller. I work for NetInsight in Stockholm. We do, well, the clue is in the name, we do network stuff like this switch there or like those. I have no idea how many CPUs are on these. Yeah, every plug-in board has at least 2 CPUs and at least 1 FPGA each. They communicate internally with redundant Ethernet. And then we combine them into large networks. Network media companies like TV broadcasters, etc., absolutely love these. They plug in a plethora of cameras from a sports arena, send the video streams to studios, and so on. We do everything. My beard is getting to the mic. We do everything. We design the mechanics, we do the electronics, write the FPGA code, low-level software, networking protocols, network management systems, the lot. So, and we also do cloud-based streaming, which I have a little bit more difficult time visualizing what that actually means. Incidentally, we are hiring. Come talk to me afterwards if you think that sounds like a cool thing to work with. Anyway, back to this, Asynchronous I/O and Coroutine. So in C++20, we sort of kind of got coroutines. It's there in the language. Everything is needed to work with coroutines. It's there, but there is no support in the library, which makes things, shall we say, painful, maybe. And if you work on Linux, which I do, if you have a reasonably recent Linux kernel, you have IO Uring, which is a technique for doing asynchronous I/O that is very low overhead and without needing to wait too much and copy data too much. So I thought, wait a minute, this is great. Something that just provides me with an asynchronous source of information that I can consume and coroutines that can just sort of loop over these in several instances in parallel. That is absolutely amazing. I want to investigate this. So I did. So let's have a look at how networking in Linux is typically made. Well, if you just listen to one socket, then it's easy. Then you just have a for loop and you do reads on that one. But if you have more than one source, you probably use select or poll or epoll, if you're modern, to register the file descriptors that you want to react on. And when any of those function calls says that, hey, data is ready for you, then you do a read or receive message or receive multi-message. And corresponding to send. And there are 2 problems with this. One is the classic callback hell. You must register something that reacts to this asynchronous event and do something. And also they are sequentialized in unfortunate ways. So typically, you find yourself writing something like this as an example, a poller that you can register file descriptors and something that does work when data becomes available. And then a wait function that does just that. It waits for some data to become available. When it does, you read them and you do some work. You probably don't have a 1500 bytes buffer on the stack. You probably have some memory pool, but let's keep the example simple. 1500, by the way, is used because what I work with is, like I mentioned, streaming of video services. Video streaming protocols are almost always based on UDP, because it's easier to just write something on top of UDP than to write a new IP protocol. And the traditional max size for the payload is on UDP is 1500 bytes. So that's sort of where that magic number comes from. So yeah, this works. So what happens is you call poll. Data comes in from the IP stack, fills some buffer that belongs to the IP stack. When the buffer is filled, you get notified that poll is done, data is ready, so you can copy it up to your buffer. And then the kernel can start working again while you process your data. And then you can poll again, waiting for the next. And you get this, as a minimum, you get system calls for everything you read, and you get copying of data, which can be expensive. Whether that cost is prohibitive for you or not, that depends entirely on what it is you do. So we can have a look at what happens when we do this. So I have a very simple program. I have this poller, exactly the one you saw. So my main is I'm just opening on localhost port 4000 and 4001. And to the poller I add, for port 4000, I'm just calculating the sum of the number of packets and the sum of the bytes in the packets. It's nothing exciting. And as soon as something arrives on port 4001, we print them all, print the information, and then call it a day. So maybe not the most exciting networking program ever written, but something. So for these examples, I'm using G++11, by the way, because it's definitely not needed for this example, but it has everything needed for the coroutines later. So if I run this through strace to see the system calls, we see the call to poll here, and we're stuck waiting for something to happen. There we are, almost. This is something, if you didn't know this, this is cool. Bash, the shell bash, has pseudo devices for UDP. So in this case, I'm writing the string foo to UDP port 4000 on localhost. That is kind of neat. So if I do that, we see poll was released, we read the string foo with the line feed. Can do another one, nothing too exciting. Go to 4001, and we're done, and we see that. Yeah, we're at 2 packets, and the sum of all bytes was 688. All right. Enter IO Uring. IO Uring is a shared memory data structure shared between your process, or actually your thread, and the kernel. You can have one Uring instance per thread in a Linux process. And the important bits there are the submission queue and the completion queue. So on the submission queue, you submit work that you want it to do. And the completion queue is how it tells you that, yeah, I'm done. And it's up to you to decide how large you want these queues to be, how many operations you want to have pending at the same time. And this works primarily, or maybe only, I'm not sure, on the IP stack or the file system. I made the mistake of registering reads from standard in and it did really not work well. It didn't fail, mind, it just didn't work. Error handling, that is great. It has two APIs, a low-level API. I wouldn't really call it an API at all, because what it is a description of this lock-free shared memory data structure and how you are supposed to manipulate it, and please don't ruin the world while you're at it. Or you can use the so-called high-level API, which in my opinion is very low-level. But it's at least a set of functions that you can call that is good. So I'm using the high-level API, liburing.h. And what you do is you create an instance. This is a C API, obviously. You create an instance and initialize it. The number 8 there is the size of these queues, how many operations I want to have maximum pending at any one time. And then when you want something to be done, you say, get a submission queue entry for me, fill it in with what operation. In this case, I want to prepare a read on this entry for this file descriptor, and the pointer and size say where the data area to get the packet payload into. And then you call this set data to associate something with it, because you can have, like I said, you can have several submissions pending at the same time, and when one finishes, you want to know what work was this that was done, and you use this set data to associate something with it. Whatever you do is up to you. It doesn't care. You have 64 bits. Use them wisely. And then you wait. You say, I'm standing here until I get something. And when I get something, fill it in this entry. And then you can look at the data to find whatever you associated with it. And it will either hold an error message, error information, actually an error no number, or the size of the number of bytes that were processed. Well, that's pretty much it. So you write something similar to the poller. You write a ring where you can add work or wait. But things are a little bit different, since we need to provide already before any job is done, you need to provide the data area. So I have this read work struct that holds the callback to send when something happens, and an array of the magical 1500 bytes. As mentioned, you probably want some kind of message pool or whatever, but let's keep the example simple. So when we add something, we create one of these work structs, store the callback and the file descriptor, get a submission queue entry, and prepare a read. And that's pretty much it. Then we are ready. Yeah, I had actually prepared those things for what I just said. Excellent. Okay, so what happens then if we look at it from a high-level perspective is that we already have the data buffers ready before we even do any calls. And then the kernel will start filling something in. We get notified that it is ready. So the kernel starts filling in the next one while we are processing this one. And then when we are done processing it, we can get a notification that the previous one was now filled. And we sort of get a multi-threaded effect here. Actually, not sort of, we do. But we have not written a multi-threaded program. We are multi-threaded between our process and the kernel. So that is neat. And there are actually fewer system calls. I'll show you. And better performance, which is easily demonstrable. Is that how you say it? So if we look at the Uring sum, have this ring structure, initialize it, and exit when done. The work, how to add work. Wait is way more complicated because we wait for an entry and then get our struct to identify what happens so we can call the callback. Then we mark the entry as seen. This tells the Uring that, okay, this data is now available to use again. But we also need to get an entry and prepare the next read, because every operation you do is fire and forget. You say, I want to read one packet, and then I want to read another packet, and then I want to read another packet. So we have to do these continuously. And then I can also, once it says something is available, I can use this peak queue, which never ever pauses execution. It just says, it just looks into this shared memory data structure and say, okay, there's one more. Okay, let's do with that one also, and we can keep going. So if we do this, it will be extremely uninteresting, but I'm doing it anyway because I'm an evil person. I want to bore you. So we see we get two calls when I pass a message. One to get into the queue to submit the request, and then we are paused. So then there's one more where we actually do something. So okay, so we get two system calls for every message anyway. What's so interesting about that? Well, we can maybe raise the data rate a bit. I'm not super fast typer. So strace is interesting. What it does is it just shows you a summary of all system calls made and how many of them. And now I can use this other really useful tool, nping. Nping, we say, so that queue, just be quiet. Send to UDP port 4000, rate 1000. Rate 1000 means, means don't do any rate limiting. Send the messages as fast as you ever can. Every packet should be 1400 bytes, send them to localhost. And then when we have done this for this count 20,000 messages, then we send to 4001 to exit the program. So we can do that. All right, so what can we see? Packets received 6,000, I sent 20,000. So this program is a little bit too slow, actually, and we see a little less than 6,500 calls to read and to poll each. That is expected. You can make this a little bit faster by, instead of using read, you can use receive multi-message, but it's still at least one system call per file descriptor. Let's do the same with the Uring. We lost some packets, but not a heck of a lot compared to what was before. And 5,265 system calls to Uring. That is roughly 1 in 4, roughly. And that can actually be seen. Why? Here. Because I sort of cheated and said, yeah, I actually want 4 entries for this port, pending at all times. So if I'm not fast enough to grab the first one when it comes, it will start filling in the next one, and then I'll start reading them. And it will start filling in the other ones. So you don't get a lot of interaction here between the kernel and your programs. This is fast. So our Uring is good. Let's pause them for a while time to change topic. Coroutines. Coroutines offers a way to write asynchronous code as if they were continuous loops. All right, cool. And we have language support since C++ 20. And what happens is that compiler uses magic to convert the code you have written into something that is completely different via types that you must write. That is an important bit. And they are mind-bogglingly hard to understand. I tore my hair out when I wrote it. And the standard library does not help. Really, it doesn't. So what happens then if we say that these are two coroutine loops? We can say that the one to the right, it suspends its execution. The one to the left computes some x. And then it suspends its execution, resumes execution to the right with this computed x, so that it can do some work with it. And when it's done, it can suspend its execution, hand over to the one to the left to resume its execution, compute another x, suspend its execution, resume the one to the right that can receive the x and do something with it, and so on. And the way this happens is, like I said, compiler magic. So we have a coroutine that looks like this, my coro. Takes an int x and y and a source. We have a loop and we co-overweight from the source. And as long as we get a non-zero value, we just add something to the result and then we return. And we create something, this a coroutine return object by calling my coro with some values and this source. And what the compiler does, when it starts compiling this and it says, oh, wait, I know what you're up to. You're writing a coroutine. Cool. So it writes it sort of kind of like this. I'm actually lying a lot now. But something like a class that takes these local variables as member variables and then calls, in this case, an operator function call with the values as they appear. And then we have a function return result. And the last line is, it actually creates something on the heap for us with the source, and we get something a little bit magical that looks something like the type that we have written. And it's really not this simple, but it sort of works as an entry-level mental model that your coroutine becomes an object allocated on the heap, and it is called with new values as you co-await values. The issue here is that we must write this type and this type, because this is something that we can co-await. So these types are, if you read what little library support there exists and some standard text, you find that they are usually called coroutine return object, which is not super descriptive. Most blog posts and presentations I've seen, they tend to call them tasks. So I'm sticking with task, whether I like it or not, just to not add more confusion. So a task will look something like this. We have a promise type, it must exist, and it is not std promise. It's absolutely not std promise, because why not take a chance to confuse matters? And of course we have to write the promise type ourselves. Go figure. And our task object is created from a promise object that is allocated for us by compiler magic. And we must take care of its lifetime. And it's nowhere near as simple that you can just delete it, because if you do that, things will go bad. Don't do that. No, you can use a coroutine deleter that uses the support from the library to say that I want a coroutine handle to this promise type. So you get this. You say, hey, I have this promise. Give me the coroutine handle for it, and you destroy the coroutine handle, pretty please. And then you've sort of ended the life of the coroutine. That was an afternoon gone. The promise type. We have to write the promise type too. There's a lot of ritual in writing a promise type. They must look sort of like this. You must have this function called getReturnObject, and this is the one that creates the task from the promise. Initial suspend and final suspend must exist. They usually don't have any body at all. They just return a suspend never or a suspend always. And what they do is pretty much what the name says. Here are actually functions that are not part of the ritual. These are convenience functions that I have decided to write to make my life a little bit less miserable. We have a continuation here. The next coroutine, the coroutine that is waiting for something to come into this promise. And the way you do this is you have this function yield value that you give it a value saying that I want you to store this value in the promise. I'm using a stud optional here. Yeah, I should mention that I'm cheating a lot here. I'm writing the absolute minimum that compiles and does the job, but you really want more if you want to use coroutines for real. So, for example, this function unhandled exception, I'm just ignoring. It's there, it's empty, it doesn't do anything. If anything throws exceptions in here, bad things will happen. Don't do this. So I usually always post the example codes I use for presentations on GitHub. I will not do this here because I don't want you to reuse them. This is just the minimum to show what I want to show today. The interesting bit is the highlighted part there, the boldface part, continuation resume. So after we have entered the value, we say resume this coroutine that was waiting for information here. And then in the task, we have this operator co-await. So when you see co-await X, what happens is that it's under the hood is a call to x.operator co-await. And it returns an awaitable that communicates with the promise that belongs to the task. And also here, a little bit of ritual. We need this await ready that typically just queries the promise to say, do you hold a value or not? And await suspend is when you decide that, no, actually, the promise does not have a value. So could you please stop running right now? So we get a coroutine handle that we store in the continuation. And some of you may feel horns growing up on your forehead here and say, wait a minute, do I need to store the continuation in the promise? Can I squirrel them away somewhere in a cooperative scheduler, maybe? And yeah, you can. And I'm sure a lot will do that. And I'm sure a few of them will actually create something awesome, and the rest will cause an incredible mess for their colleagues. So I stick with doing it simple. Say that there is one or no coroutines waiting for something on a promise. So I have my promise.continuation. And finally, something to actually get the value from the promise. And this one does, it reads the value from, I stored it in an optional. So just read the value from the optional, clear the optional, return the value to make it empty again. So let's try to see what happens when we try to write and use a coroutine. We can ignore these helpers that help me be sane. This is all the same as you saw, except that I've instrumented it with several tracers just to show what is happening here. So we can see when we get a call to get return object, initial, suspend, etc. And the same with the task and all its functions. But in the end, we can do something like this. We have something that I choose to call incoming, that is a task of ints that we make. And make really just does, it's a static function that returns a task and immediately suspends. That is the only thing it does. So we have something incoming here, and we have our print all. That is this coroutine that just, we trace that, we enter it, read values, and print them as they arrive. And then we print when we exit. And then I've done so that on my tasks, I can ask for a reference to the promise. So if we call promise yield value, it will do all this dance that I mentioned. So if we run this, we can see a lot of things. So the first things that happens when we call this incoming make, we see that it creates the promise and calls get return object on the promise, which creates the task. And then it calls initial suspend, and then we suspend execution. And then we go to the print all that creates a task for the printer. I call it printer. Does the initial suspend, which suspends it, which does not suspend it, sorry, it's suspend never. We see this print all tracer, and then it goes to co-await, which means that it calls co-await on the task, which calls await ready on the awaiter, which calls is ready on the promise, and it says 0. No, I'm not ready. Sorry. So we get an await suspend, cannot go, sorry. So now we're back here and call yield value 4, which calls await resume, so that the function can call get on the promise, and the coroutine can print 4. And then another loop. And then at the end, destruction of all the tasks and promises. What is not visible though is this trace print all done. Because I have actually not exited this loop. You remember this mental model simplified image of an object that is created on the heap, where you break the loop such that it is instead the compiler that magically calls a function call operator. And what happens is that it was waiting for the compiler to call the function call operator, but it actually didn't, it just deleted the object. So we never exited this loop, so we didn't see this one.
So if you would have forced one more call, you would have gotten.
No, if I had some kind of criteria to exit the loop. So for example, I could have said that if, well, a stupid example, say it's a magic number, if I get a 0, I will exit the loop, then I will get it. Sorry for those who didn't hear, the question was if I had done one more operation, would it then have printed the print all done? That's a heck of a lot of work for not doing much, I think. But we can go on. we can write a filter, something that a coroutine that takes a predicate and reads values from some task and emits them back. So what we do, we co-await with values. I should probably remove that. Co-await values. For every value, we call the predicate. If the predicate is true, we co-yield the value. And co-yield means to call the yield value member function of the task that is associated with, or on the promise that is associated with the task. So the name yield value on the promise was not entirely arbitrary. It is what the compiler will generate code to call. So what we can see now is one thing, is that there doesn't have to be a one-to-one relation between what we get from co-await and what we hand over with yield. We can collect several values with several co-await. We can actually co-await from several different sources if we want to, but we can only co-yield to our own coroutine return object, our own task. But this is not worthless in any way. We can write a program like this where we have our incoming as before. We create we call filter in with this predicate is odd on incoming, and so we get a task that we call odd values. And then we can call print all on the odd values. And the print all is the same as you saw before. And then we can just do a loop and say, call yield value for all of these. So let's have a look. So, yeah, pretty much the same code as you saw before. It should be exactly the same, actually. But who knows, computers. And we see the odd values, entirely surprising. But now something is beginning to happen, I think. Writing those tasks, those promise types, the awaitable, is not a lot of fun. But this is actually a little bit interesting, I think. Because we now have two things that would normally be a set of chained callbacks. But we're writing them as individual loops where we get our values and do something with them and hand them over and do something. So we're beginning to see that maybe all this work can pay off. Maybe. So let's marry these two together, because that's what this presentation is about. So we have seen how Uring offers asynchronous data and with low overhead. We have seen that you can call yield value on a coroutine promise to push information through the coroutine pipeline. And we have seen how to read values from an upstream coroutine with co-await, and how to pass forward values to further downstream coroutines with co-yield. So let's put these together. So here's a slight convenience thing, higher order function 2 promise that I'm just using to get a callback that calls yield value for packets. And since I'm an extremely lazy person, I said just auto on packets so that I don't have to rewrite the code if I choose to change the signature of my callbacks from the ring. So we can have something, a coroutine. We read packets from the socket on port 4000 localhost. We want to count all the packets because that's a good statistic to have in any networking system. So we can write a simple coroutine that takes a task of span of char, because that's what we want the data to be, and just loops over them and updates our two counters, the number of packets and the number of bytes in the packets. And then we co-yield it to send to the next level. And then actually, I don't want to work with spans of char. I want to work with strings. So I want to convert these to strings. So I have a coroutine to string that takes a task of span of char and gives me a task of strings. So I just co-await these packets that are spans and co-yield the creation of a string from these. Since begin and end are iterators to char, to const char, that works fine to create strings like that. And then we saw that when I, from the command line, used echo to the pseudo devices in bash, we got a pending new line, which we don't want. So let's strip those. So we have another coroutine that just takes a task of strings, co-weight them, and as long as they end with a new line, we strip them. And when there are no new lines remaining, we co-yield the results. So pass it on. And then maybe we want to print these, want to work with them in lines. So we want to concatenate them to 40 characters. So now I have a coroutine that retains state between the iterations. So we have a current line. Sorry. We have a current line that we co-await a string from in, and if the concatenation of the current line and the new string is too long, we co-yield the old string and store the new one as our next piece. Otherwise, we just append to our current string, make it grow. And then we can get to the last one that prints lines, and I'm deviating a little bit from the previous print all so that I can just to have a clear, distinct definition of where things are. So I'm reading lines and I'm printing them with colons on each end so we can see where they begin and end, and print with a new line also. And the rest is like before. We add to the port 4000 that this called toPromise that just converts a function call into poking the promise by calling yield value to push things in. And on 4000, I still have the old print and exit. So let's do this. What was it called? Uring IO, of course. So we have all these coroutines that you saw before. And yeah, I'm adding 4 of them at a time, completely unnecessary, but why not? So if I do this, the full name. So I'm just taking all the names of my dev, read them and pass them on to this localhost port 4000, and when done, end it all by writing something to port 4001. So let's do this. Bonk. Oh no, I have shared secrets. You have now seen what devices I have on my computer. But this is actually pretty neat. These steps of computation where each is just a loop, where you do some work. This is, of course, a very silly example, but that's because I don't want to complicate matters by calling FFmpeg libraries and do image work or whatever. So I kind of like this, but there's no doubt that I omitted a lot. Like I mentioned, this is pretty much the minimum amount of code that you can write that compiles and does the thing without, to my knowledge, have undefined behavior. Error handling is really not trivial. Really, really, really not trivial. And I choose to not even touch it. One thing that I did mention, you have this unhandled exception function that you really should implement and do something with. But other things, also cancellation is tricky. One thing is if you want to cancel the entire computation pipeline, then it's easy, just destroy all the objects, bang, done. But if you have a situation where some coroutine in the middle of the pipeline says, okay, I'm done, that is not an obvious thing how to handle, unfortunately. And IO Uring is also interesting because you have a lot of pending operations that use shared memory that belongs to your program. If you deallocate them while they are pending, bad things will happen. Guaranteed. Very bad things will happen. So you need to think about these. And also, those of you who were here for the previous presentation noticed that while there were many things really similar with those coroutine types and mine, they weren't the same. They differ. There are so many ways to do these. There are so many things to tweak. And what's really confusing, I think, is that when the compiler sees your coroutine types, the task, the promise, and the awaitable, it will inspect the code and see, you have that function. Okay, cool. And it has this signature, not that signature. So then I will generate code that does these things. So that is interesting, I think. So yeah, very minimal example. Some conclusions. Lack of library support is a huge headache. There's no denying it. Writing these are not fun. They aren't. Testing and debugging is absolutely terrible. It's absolutely nightmarishly difficult. I mean, sure, if you have a bug in a coroutine where you're awaiting something and do something, that is fine. You can have a breakpoint in a debugger there and do things. But if you have a problem in the communication between coroutines with these promise types, etc., then you are in a very unpleasant situation. I know this because I have been there. What I did, this was really a lifesaver for me. This is a extremely simple constexpr string class that can be used as a non-type template parameter, which I'm using for tracing. So on my promise, I have actually a name for each of them. And I have these kind of tracers say that task T with this name, get return object was called. And I'm using these names, print lines, to say, yeah, it's a task void one. I call it print lines. And it takes some other task with some name. And this means that when something goes really, really, really wrong and yield value crashed, and I say, okay, yield value, cool, I have 8 objects with yield value, which? Then I can at least see, it was the filter in yield value that crashed. Okay, now I have at least some clue. This is 1980s debugging. This is horrible. We should not need to be there. Sorry, but this is the best I could come up with. And it's terrible, I'm sorry. But writing these asynchronous code as if they were local loops is undeniably convenient. And connecting pipelines of computation is really powerful, like we saw in this last example. It's a silly example, but just seeing how you can chain loops that do work, that is nice. That is really nice. Some resources to look into. Shoaib Hussain, this Lord of the IO Uring, I find this, it's a fairly good documentation, I think, on how to use the IO Uring APIs. There are places that are lacking information, but on the whole, it's good. On learning coroutines more, there's a plethora of information on blog posts and conference presentations, etc. The one that worked for me was Pavel Novikov's Understanding Coroutines, by example. That was the one that made a click for me that, okay, that is what's happening. So, thank you, Pavel. Work great on. Lack of standard library, lack of library support. Lewis Baker has one called CPP Coro. I'm a little bit, I don't know what the state of that is. It looks, if you look at the GitHub repo, it doesn't seem to have been touched for a couple of years. So I'm not sure. Mikhail Svetkin, who presented just before me here, has this EC Coroutines. Worth having a look at. I learned about it only just before I entered stage, so I haven't gone into any details, sorry. But I thought your presentation was great, so it's probably good. Yeah, Mikhail says it's tiny, so don't have too high expectations. Another really interesting library is libunifex, Facebook experimental, it's open sourced. It uses coroutines and it uses IO Uring for doing network IO. I have not gone into details about it, but I think it looks super interesting, actually. At least the ideas from it. Maybe not all the details, but definitely the ideas from it. And that was all I have to say. That was Asynchronous IO and coroutines for smooth data streaming. I'm sorry if I sounded more optimistic in the beginning in the title than I intended, or well, I actually did intend to be that optimistic, but I couldn't. Here's how you can find me if you want to, and thank you all for being here. And we do have a few minutes for questions if you have any, or are you stunned? Yeah. What is performance like if I have enabled optimizations? I'm sorry, I don't know. I haven't measured, is the answer. The one thing I can say from just generic experience is that at least if you compare with a threaded solution, if you are doing work that touches a lot of data, you will get better cache locality. But otherwise, I don't know. Other questions?
So you showed the queue depth of 4 packets
Yeah.
in the receiving example.
Yeah.
That seems really shallow. Did you try to up that a little bit to see if you could not drop any packets?
Okay, so the question was, did I try? I used only 4 packets in the performance example, and have I tried more because 4 is very shallow? The answer is no, I have not tried, but let's do that. We have several minutes. And now I will have to do something about the ring because I initialize it only to 8. Let's do 18. and do the nping thing. What did I miss? Yeah, we got everything. No, okay. No, what I missed was strace has a non-trivial overhead, so we should be fair. So let's do this again. No, strace-c, otherwise it's obviously lousy. We lost a few. Didn't matter. I think it's the overhead from strace actually that causes the losses in this case. Yeah, there are fewer system calls. Yes, that is correct. Yeah, there is less overhead per packet. Yes, that is true. More questions?
So this enables you to make almost in-place streaming pipelines, right?
Yes.
Ranges was just approved. I don't think anyone really used the IPO database. I would assume that with good library support, even ranges could be parameterized and or better.
Okay, ranges and coroutines. Yeah, yeah. Now pause. Sorry, I'm not going there. So, other questions? All right. Thanks again.